So this is some of the observational data that has been accumulated over the past few decades, which has brought us from speculative cosmology into the era of precision cosmology. Let's put it together and see how, using this information, cosmologists have constructed the parameters of the standard cosmological model, which goes by the name lambda cold dark matter, lambda for a cosmological constant, cold dark matter because the dark matter is in the form of high mass non-relativistic WIMPs as opposed to, say, neutrinos or light relativistic particles. This is to do with the way that they would clump, but it has other implications that we will see. So what have we had? Well, here is a plot from 2011 that very nicely shows you how we have learned what we know about our universe. So what do we have? Well, the supernova survey, remember, it measured the deceleration parameter. That was the most precise way of saying what to first order they were measuring. And we wrote that as one linear combination of the present densities of radiation, dust, and density parameters of radiation, dust, and the cosmological term. And so what that means, of course, I'm going to set, we know the density, energy density in radiation, we know it's very small. So if you ignore those two, you see that if you only had a supernova survey, you would know this linear combination, but there would be a sort of degenerate direction. So this over here is what the supernova survey tells you. It tells you that a half of, in this plot, we're plotting omega m, which is what I call omega d, on one side, and omega lambda on the other. And what the supernova survey, as you can see, tells you is that this combination, a half of omega d minus omega lambda, is constrained to within very narrow ranges. These ovals on these graphs indicate areas outside of which we can, with increasing confidence, exclude those values of the parameters based on the data. And so the supernovae basically constrain you to lie on this kind of a line where this combination is constant. On the other hand, we said that acoustic oscillations, as discovered in galaxy clustering and in Lyman alpha clustering, is pretty much sensitive to omega d. So it constrains you to this roughly vertical line over here, suggesting that the total matter density is around 0.3. And then the cosmic microwave background data fundamentally gave us the statement that the universe is flat. That is sensitive, again ignoring the radiation, to the sum of the density parameter of dust and of cosmological constant. So it constrains us to lie on this line where omega dust plus omega lambda is equal to 1, or near this line over here, which is the line that constrains us to flatness. You see that I was a little bit imprecise in discussing what the cosmic microwave background does. These are three lines in a plane, and in general, three lines in a plane need not intersect, but we are gratified to discover that our three lines do intersect. They intersect in a very narrow region, and so because of this, by combining these three pieces of information, we can constrain the parameters of the universe to this rather specific values that I produced. I didn't give you error bars because computing them is very complicated. It is also true that I have vastly oversimplified the situation. As I said, higher peaks of the CMB, we'll talk about it, give us further data that has been used to produce these constraints. Similarly, you can use the baryon acoustic oscillations. You see that we're not constraining purely omega d, and there are other pieces of information that we get, for example, from just the baryon density given by the Lyman alpha forest, and what we understand about the light to mass ratio of various objects in the universe, and using that to predict the density of dark matter, and so on. The net result of pooling all of our information together, and I should notice that this is circa 2012, and these parameters move a little bit, is these are the post-WMAP, but pre-Planck mission, best values of the parameters. They have moved a tiny bit since then. This gave a T0 for the age of the present universe of about 13.7 billion years. Planck has nudged that to 13.8 billion years, slightly shifting these parameters. We see, again, the pi roughly corresponding to these data. I didn't find a pi chart that exactly represented these data with about 0.74 density parameter in dark energy, the known density in radiation, and slightly under 5% in baryons, and slightly over 25% in dark matter. This corresponds, when you plug in the information, this leads to a Hubble parameter of 71 kilometers per second per megaparsec, and a critical density, as I gave before, of 1.5 proton per cubic meter squared. This is our universe, and now I have retroactively justified all of the statements I have made about when the universe turned over from radiation dominated to matter dominated, or from matter dominated to cosmological parameter dominated. This is what we know. Based on these claims, I can make the astonishing claim that 74% of the energy density in the universe is indeed in the form of dark energy. How did we find this? We find this by first computing the total energy density, then separately measuring the energy density of radiation directly, and the energy density in dust rather indirectly through various cosmological measurements, and then basically saying that dark energy is the only possible solution. One can do a little bit better. One can say the missing energy density is in the form of something, and then parameterizing how close the equation of state of that object needs to be to the equation of state of dark energy. In other words, how precisely can we relate the pressure, the negative pressure that is obviously needed to accelerate expansion from this crazy other stuff, to its energy density, and by now the relation that would specify that this additional stuff is precisely dark energy and not some other weird kind of matter we hadn't understood yet, is quite narrowly constrained. So we know that this is our universe, and in particular it is flat. This might be time to answer the question that I said I would address early. I said the universe is very nearly flat, and you remember that an open universe, a negatively curved universe, a hyperbolic space, would be necessarily open, I said. A constant surface of positive curvature, a constant space, three-dimensional space of positive curvature would be closed and compact, would be a three-sphere. There would not be an infinite distance. You could not have two observers as far apart as one wishes. What about flat space? It's sort of a flat space bridges the gap. Is it possible? It's certainly possible to have a space that is infinite and flat. We know it. This is plain old three-dimensional Newtonian space. The universe we live in, and that's what could be, and I'm going to assume for the rest of these clips that that's what it is, could be just flat Newtonian space where two observers can be as far as they wish from each other. That is certainly an example of a flat three-dimensional space that is homogeneous and isotropic. Are there others? It turns out that yes, it is possible to have spaces that are three-dimensional and flat, but not infinite. In other words, two points cannot be at arbitrarily large distances. If you want them to also be exactly isotropic, you might have a problem, but you can have cases where the violations of isotropy occur at arbitrarily large distances. What's an example of this? Well, this sheet of paper that I'm holding is an example of a flat space. It looks like the Euclidean plane. Distances between the points are fixed, and you'll notice that without either bending the paper or tearing it, I can roll it up into a cylinder. Now I have a cylinder, and what I've demonstrated is that a cylinder is flat. On a cylinder, if you imagine that this sheet of paper were infinite in this direction, then you have one direction that is infinite and one direction that is finite. It's periodic. You go around and you come back to where you were before. Now, I could, in principle, take this piece of paper and bend it until the other direction were finite as well, essentially produce the shape of a donut. To do that, I would have to stretch the paper. It turns out that that is an artifact of trying to build a donut shape in three-dimensional space. Intrinsically, the surface of a donut, if you only know about the surface, can be described as a flat space. Now, of course, on this space, isotropy is not precise. This direction is different from that direction. But we measure that space is isotropic. Could it be that our space is a donut of some sort, or a three-dimensional analog, a flat three-dimensional analog of a donut where you go in some directions if you go in some directions, you will come back to exactly where you were. The answer is yes, this is possible so long, I mean, it's not excluded by experiment, so long as the distance you'd have to go before you come back is much larger than the 62 billion or the 46 billion light years that we can see, because we see no sign of that in the universe we observe. But it's mathematically consistent. If the radius of each of these dimensions were 1 trillion light years, then the violations of isotropy that this entails would not be visible in any of the observations we have made. So we do not really know about the topology of space. We at the moment have no tools with which to study it. We only know that all of our observations are consistent with space being open and infinite, Newtonian three-dimensional space with a metric that expands distances, such that distances grow according to the scale factor. We will assume that as the simplest solution for now, and perhaps someday we will be able to know more.